Welcome back. In the last class, I gave you the 555 timer, a stable multivibrator, circuit diagram, and we improved the duty cycle by different configurations, external connections. Then we got duty cycle whatever you want. Ultimately, for square wave, we need 50% duty cycle. Then we got it by having PN junction diode in the charging path, and the PN junction diode will be reverse bias during discharging path. Therefore, we are able to get 50% duty cycle. Okay. I hope this is done. Over. Okay. Now write down sawtooth waveform generator. We can get sawtooth waveform generator using 555 timer. Why do you need sawtooth waveform? What is the application of sawtooth waveform? What is sawtooth waveform? When it is charging, it will charge linearly. Discharging, it will discharge very suddenly. Again charging linearly, discharge suddenly. Charging linearly, discharge suddenly. That is what your sawtooth waveform, right? Then if you want to charge any capacitor linearly, what do you need? If you know that problem is over. Because if you take case 1, your discharging is faster. Therefore, with minimum time you can discharge. Therefore, that is fine. But charging, we are charging through resistor. When you are charging through resistor, your capacitor charges exponentially. But I want linear charge. If you are able to charge your capacitor linearly and discharge very fast, then that is nothing but your sawtooth waveform. Therefore, how to get sawtooth waveform or how to charge your capacitor linearly? If you know that point, just change the configuration, which is nothing but case 1, you'll get sawtooth waveform generator across capacitor. Okay, write down sawtooth waveform generator. But still it is a stable multivibrator only, but you will get sawtooth waveform generator. Free running oscillator. We don't have any external input, but we are getting output and the frequency whatever you want. What is frequency? Frequency is 1 by time period. Time period is equal to on time is equal to on time plus off time. Okay. Now, if you see here the voltage across the capacitor is, right, let me erase, but you have to draw once again. I'm just going to take this is as reference. This is your original stable multivibrator. Therefore, a stable multivibrator, you can say sawtooth waveform generator. Here this is sawtooth waveform generator. What is the application of sawtooth waveform? This is what we use when you consider your CRO, cathode ray oscilloscope. It is associated with horizontal plates and vertical plates, right? Therefore, whatever horizontal plates you have, it has to have, because to sweep in the sense, whatever signal which you are getting in x-axis, right, the x-axis signal variation, that is what is through horizontal plates, and whatever signal you want to observe, that is what is with respect to time. Therefore, y amplitude, the magnitude part, that is what we have to apply to vertical plates. For the vertical plates, people apply the signal what you want to observe. For the horizontal plates, we have to apply sawtooth waveform. Therefore, you see the sweep in the display, whatever CRO display you are seeing, the sweep with respect to time, that is due to horizontal plates sawtooth waveform. Therefore, we need sawtooth waveform. This is one of the applications of sawtooth waveform. Now, how to get it? Now, if you see voltage across the capacitor, right? This is nothing but voltage across the capacitor. Charging through R, charging through R, discharging through your transistor on resistance, which is minimum. Therefore, if you ask me what is VC, voltage across the capacitor, only voltage across the capacitor. I don't bother about anything. Therefore, this is what is VC. Now tell me, initially it is charging, okay, that is fine. Therefore, now if you see periodically it is charging exponentially, discharging very fast, right? When it is discharging very fast, it is discharging. Again, it is charging exponentially and then discharging very fast. Therefore, this is what your discharging time and this is what is your charging time. Therefore, this is what your charging and this is what your discharging, what it may be. This is what your discharging. But here the limit is nothing but what? This is 2/3 VCC, and lower limit is nothing but lower limit is nothing but 1/3 VCC, right? Therefore, is it sawtooth waveform? No, sawtooth waveform is sawtooth waveform. We'll call it a sawtooth waveform provided the charging time or the charging of your capacitor should be linear, but it is not charging linearly, right? This is what is our charging, and this is discharging. Discharge is very fast, okay, that is fine. This is what is our discharging path, discharging phenomena. Now, how to make the second one? How to charge capacitor linearly, right? The concept is you take a capacitor, right? This is what is our capacitor. If there is a current which is what is flowing through the capacitor, then tell me what is the voltage across the capacitor. Then the voltage what you get, voltage across the capacitor, VC. What is the relation? We know that voltage across the capacitor, VC, is equal to 1 by C integration of I into dt. We want the voltage to be increased linearly. Qualitatively I can explain. What is the reason to get voltage? The charge. If you put charge, let us say you are putting positive charge, then the positive charge is increasing, electric field is increasing, the voltage will increase. If you put same amount of charge per unit time, then the charge development will be linear, then the electric field development will be linear, then the voltage development will be linear. Simple. Therefore, the charge per unit time, whatever charge you insert per unit time, if that is constant, or I can say constant current, what is rate of flow of charge? Per unit time, if you put same charge, then your current is constant. Therefore, if current is constant, if the current which is what is flowing through the capacitor, if current is constant, then what is your capacitor? Voltage across the capacitor, VC is equal to 1 by C. Let us say that I is nothing but capital I, which is constant. We represent capital letters for DC or constant values. Then what is this? I is out. Then you will get 1 I by C integration of dt. You will get time t. Therefore, you are getting I is constant, C is constant. Then into t, what you get? You will get voltage across the capacitor linear. Therefore, now if you ask me, this is time t, and then voltage across the capacitor. Now this is what? Now what is the slope? The slope of this is nothing but I by C. This is what is the slope, if I is constant. Therefore, if you can charge your capacitor with constant current, then the voltage across the capacitor will be linear. Okay? We have to charge the capacitor with current source. If you charge the capacitor with current source, that's why if you ask me, right? Therefore, if you charge the capacitor, let us say this is what your current source, network analysis. Okay? Then you are charging the capacitor through current source. Then I am asking what is voltage across the capacitor. Now the voltage across the capacitor is what? Now the voltage across the capacitor will be, it is charging linearly. Till what time? Till what time you have current, the voltage will increase linearly till infinity also. This is ideal scenario, right? This is what is voltage across the capacitor. When you are charging your capacitor with ideal current source, you will get linear charge across the capacitor. Okay? This is what I am going to use. Therefore, how to charge capacitor linearly? If you pump constant current, you will get it. Therefore, what I do, instead of a resistor, I can put a current source. If I put a current source, the charging will be what? It is not through VCC RC, then it is directly through current source. Then the voltage across the capacitor will be, it is same, but instead of non-linear charge, it will become linear charge. But still threshold voltage will be 2/3 VCC, 1/3 VCC, 2/3 VCC, 1/3 VCC. That won't change from your 555 IC. But only the charging phenomena or the charging way or the type of charging will change from non-linear charge to linear charge. Instead of resistor, if you put a current source. Done. Therefore, if I make it, therefore this is what is your 555 IC. Okay. This is what is your 7, 6, 2, 1 ground. This is what is your output. This is 8, 4, active low VCC, right? Now if you see here, this is what is now, instead of a resistor, now this is what is a current source, then this is what it is. Now this is what your discharge. Therefore now your capacitor is charging through a constant current, you can call it as I bias, some bias current, therefore you can charge it. Now tell me what is voltage across the capacitor now. Now the voltage across the capacitor, this is what is VC, okay. This is charging path. And where is discharge path? This is what is your discharge path, okay. This is your discharge path. This is your discharging path. That is 7. 7 is always discharge. This is what is your discharge path. Now if you ask me what is voltage across the capacitor, the voltage across the capacitor will be, okay, initially it charges linearly, it is trying to charge to VCC, but it will discharge. This is what you will get, okay. This is what is the initial time. Therefore the limit is 2/3 VCC, 2/3 VCC, and the lower limit is 1/3 VCC, okay. Therefore if you neglect, therefore if I take, this is what is our on period, this is off period, on period, okay, off period. Therefore this is kind of sawtooth waveform, charging linearly, discharging very fast. Therefore this is nothing but charging, and this is nothing but discharging. It discharges very fast because of on resistance of your BJT, that charges very. Therefore this is nothing but your sawtooth waveform. If you ignore first half cycle or full cycle, right, then it will go whatever may be. This is what is your sawtooth waveform generator. This is sawtooth waveform. This is your sawtooth waveform. Okay, take it. See, whatever you want, you can get it. Tell me, once you get square wave, can't you get triangular wave? Yes, we can get triangular wave, right? Here only we can get triangular wave. You have to add opposite current source. Opposite current source when it is discharging, then charging, discharging, charging, discharging. You will get triangular wave also from this. Okay, enough. Once you understand these things, we have multiple circuits we can get using 555 timer with respect to clock. Clock means the clock can be square wave, triangular wave, sawtooth waveform, right? Anything. Impulse generator, once you get square wave, pass it through differentiator, you will get impulse train. I'll give you 1 more minute time. Try to complete in a minute. Then I'll explain monostable multivibrator. With that I can say 555 timer is over. Okay. And I'll explain the application of monostable multivibrator, which is nothing but pulse stretcher. Whatever triggers you are giving, that is nothing but input. Then we can stretch it and then we can get it. Okay. Whenever you get a control signal from microcontroller, which is very small trigger, but if you want to know and if you want to get some light out of it to represent the trigger, people use stretcher, pulse stretcher. Whatever trigger you are applying, that will be stretched if you apply to monostable multivibrator using 555 timer. Okay, that part I'll explain. When I explain monostable multivibrator in the case of op amp, right, I didn't explain the application. I think the same application is valid here also. Let's see what is it. I think within this session, the topic 555 timer is over. Then I can say the concept and the classroom workbook problems related to chapter 4 can be completed in this session. Then we can see workbook problems. Then after that, we can go for chapter number 5. Chapter 5 will not take that much time. Okay, those are all related to diode. Then I already explained the technique to solve the diode problems. Just we will solve the problems blindly. Workbook problems, classroom workbook problems, student workbook problems. Then we can go to chapter wise problems and subject wise problems. Okay, the test whatever you are going through, we will see the solutions for chapter wise tests as well as subject wise tests. I think we are almost close to completion of the syllabus. Couple of sessions are required to complete. Okay, chapter 4 is the one which took more time. Chapter 2 BJT amplifiers also took more time. Okay, because many concepts are included inside chapter 4. That is what I categorized related to op amp. Wherever op amp is there, we can categorize into chapter 4. Done. Now write down monostable multivibrator. Monostable multivibrator. Actually I can use pin diagram to describe, but it's better if I give you complete circuit diagram as well as pin diagram. Okay, monostable. Now the trigger whatever I told, right, that will come into picture. Okay, just listen. Again we have two op amps, right, they are acting as a comparator signals. Okay, now we have two op amps, minus, plus, minus, plus. Okay, now we have a resistor, this is ground, this is reference generator which is there inside your 555 timer. Okay, now this is what is your reference and this is what is your reference. Okay, this is 1/3 VCC and this is 2/3 VCC. Okay, this is what is our VCC. Right, now these two outputs are going to your latch. This is SR latch. Now this output is going to your transistor. We have your transistor, that is what your discharge path. Okay, this is what is ground. Now we have an inverter, let us say, and this is what is our output. This is terminal number 3 that you know, and we have transistor. This is what your reset and this is what is your power supply. Again, last time also I did like this, now also I am doing this. Okay, just to do not have. Okay, now this is what this is your NPN transistor. Now this is what is your terminal number reset. This is terminal number 4. Okay, This is PNP transistor. Now, reference, right? We know already. This is what is your, this is threshold, and I told this is what your trigger. This is what your trigger. Now, and this is what your discharge. I am going to write configuration 1. Now, if you observe clearly, now external components. When I say external components, it is what is having what? It is having resistor. Then wherever you have capacitor, this is what, right? Then this is what is connected to, the discharge is connected to this, and threshold is also connected to this, but the trigger is not connected. The trigger is having external input, one more input. Therefore, this is what is your trigger. Therefore, this is trigger. That's why this is what is called trigger. Number 2, and this is what is your threshold, which is number 6, and this is what is your discharge, number 7. Okay, and this is what is your ground, number 1, and this is what your supply, number 8, number 4, number 3. I'm not representing 5. This is 5. Okay, that's fine. Now, if you observe clearly, again same thing. This is what your R, and this is C. Now, this is what your external input. This is what your external input. Okay. Always, if you see here external input, this is what your trigger. Because this is monostable. Why it is monostable? Let us say this is what is having VCC. That is what is having VCC. If there is no trigger, it is having VCC. Let us say this is what your VCC. Therefore, now let's see the timing diagram. Okay. Now, if you understand the timing diagram, that is over. Okay. I'm not going to derive anything. Just I will tell you the application and how it is acting as a monostable multivibrator. I will explain. Just listen. Now, first of all, voltage across the capacitor. If you take voltage across the capacitor, this is what your time t. Now, this is voltage across the capacitor. Initially, let us say voltage across the capacitor is 0, right? Therefore, this is what is voltage across the capacitor. This is what is VC. Initially, voltage across the capacitor is 0. When this is 0, right? Initially, voltage across the capacitor is 0. Right? When this is 0, now let's see. What is this voltage? The trigger voltage is VCC. Initially, the trigger voltage is VCC. Then VCC, 1/3 VCC, which is more? Minus is more. Therefore, this is initially 0. Now, initially this is 0. Which is more? Minus is more. This is 0. Let us say 0 to 0. What you get? Therefore, 0 to 0. Previous state. Let us say the previous state is 0. Then you are getting 1 here. Your output is 1. Okay. Your output is 1. And the 0, it is off. Therefore, your capacitor is charging. Your capacitor is charging. Okay. Now, if you see here, your capacitor is charging. Therefore, this is what your capacitor is charging. It is trying to charge to what? It is trying to charge to VCC. When it is trying to charge to VCC, same thing. It is trying to charge to VCC. But once it crosses, same thing, 2/3 VCC. Once it crosses 2/3 VCC, what will happen? Once it crosses 2/3 VCC, let's see, set and reset. Okay. I think that is not required. Directly I can tell you what will happen to Q. Directly I'll give you Q, then we will see output. This is what is Q. Then I'll explain trigger. This is what is our trigger. And finally, the output. Okay. This is what is your output. Therefore, initially output is 1. This is 0. This is 1. Therefore now trigger is 1. Let us say this is what is trigger. This is VCC. This is 0. Let us say. Okay. Therefore now what is your output? Output is 0. Your output is 0. Q is 0. Once it crosses 2/3 VCC. Once it crosses 2/3 VCC. Therefore capacitor is charging. Therefore once it crosses 2/3 VCC. When this is what is increasing. Right. Then this is what is having. When this is what is crossing 2/3 VCC. Then plus is more. When plus is more. Then this will be 1. Set will be 1. When set will be 1. Your Q will be 1. Therefore your Q will be 1. Once it crosses 2/3 VCC. Your Q will be 1. When Q is 1. When Q is 1, what is your output? When Q is 1, your output will be 0. Your output will be 0. Okay? And this is what it is. Therefore, Q is 1. Then, when this is what is going, once it crosses, right? Then, transistor is off. Sorry, when transistor is on. When Q is 1, your transistor is off. When transistor is off, what I am saying, once it crosses greater than or equal to 2/3 VCC, momentarily it will become 1. This is VCC only. This is 0. Right? This is what is the starting point. Okay? This is always VCC. Okay? Now, this is 0, 0. Therefore, set is 1. Then your output will be 1. When this is 1, it will be 0. Right? When it is 1, your capacitor will be, this is discharging. Therefore, this is what is on. When this is what is on, it will be discharging. It discharges very quickly. When it is discharging very quickly, it is trying to discharge to 0. Yes, it will discharge to 0. Why? Even though it crosses 1/3 VCC, earlier when it crosses 1/3 VCC, it used to trigger, this comparator used to trigger and then it used to give a reset. When you say reset, it will be 0, then transistor will be off and then you start charging. That is what we have seen, 2/3 VCC, 1/3 VCC, 2/3 VCC, 1/3 VCC. But now here, the trigger is given always VCC, this is always 0, even it has 1/3 VCC, doesn't matter. Therefore now the state is stable. Remember, this state is stable. Whatever output 0 you are getting, this is what is stable. If output is 1, unstable, this is what is unstable state. This is unstable state. But now whatever you are getting is stable state. Therefore this is what is your stable state. Your capacitor will be 0, it is there lifelong. Your Q will be 1, your Q will be 1 continuously. Therefore nothing is happening. And then this is what it is. Right? Therefore you went to stable state. Therefore 0 is nothing but your stable state. This is stable state. It will stay there only. Okay? It will be 1 only. That's it. Now I want to change the state because now it went to stable state. Stable state means it will be there like that. Now I want to change the state. If I want to change the state, what to do? We have to apply a trigger. We need to disturb the state. If I want to disturb the state, what to do? Now your transistor is on. It is completely discharged. Done. I want to release. I don't want 1 here. I want 0 here. 0 means I want reset. I want reset means it should be 1. It should be 1 means it should be less than 1/3 VCC. Now I need to apply trigger. Whenever you want to have, just apply trigger. When you apply trigger, you can say this is what is 0. Actually 1/3 VCC, that is what is enough. Therefore, if it is crossing 1/3 VCC, that is what is enough. When this is what is crossing, whenever you apply trigger now, therefore stable state. Until unless you apply trigger, let us say I am applying the trigger. Once I apply trigger, which is very small pulse, right? This is what your trigger pulse. This is what your trigger pulse. Once I apply trigger, then what will happen? Then immediately, momentarily, this will become 0 or less than 1/3 VCC. When it is less than 1/3 VCC, then plus is more momentarily. Then this will be 1. When this is 1, reset will be 1. When reset is 1, your output will be 0. When output is 0, your transistor is off. When transistor is off, your capacitor will be charging. Therefore, now it is entering into stable state. Then, whenever trigger applies, okay, it came out from stable state to unstable state. Therefore, it will go up. It will enter into unstable state. Again, when it is entering into unstable state, whenever trigger applies, right? Whenever trigger applies, your output will be immediately your output will be right, your output will be 0 whenever trigger applies. Okay, Q will be 0. Now your capacitor starts charging. Your capacitor starts charging. Again, when it charges 2/3 VCC, it is trying to charge to VCC. When it charges 2/3 VCC, then you know, again the states will change. Then your output will be 1. It is VCC. Then it is becoming 0. Therefore, it is unstable. This is unstable. This is stable. Then what will happen? Again, until unless you apply trigger. Let us say I am applying trigger here. Therefore, whenever I apply trigger, exactly that point your output will change from stable state to, now this is what is stable state, it will enter into unstable state. Then again, whenever trigger applies, okay, this will be completely discharged. Whenever trigger applies, then only your output will change. Then again your capacitor start charging. That will continue, right? I'll stop. Therefore, if you observe clearly, this is what is stable state. Now it is stable state. This is what is our stable state. This is stable state. This is unstable state. Okay, this is what your output, right? Maybe if you want exactly, if you observe clearly what is the application of this, whenever trigger applies, then only your output is changing, Q is changing or output is changing. Your output is nothing but Q bar. This is Q bar. This is your Q bar. Okay. Now, therefore, whenever trigger applies, then output is changing. Again, it is coming to 1. Again, whenever trigger applies, therefore your output is changing. If you observe clearly, right, if I continue for one more cycle, okay, it will be discharged immediately. Okay. Then again, when you apply trigger, whenever trigger is applied, okay, until that trigger applies means it will be 0. And after some time, it will be 1. Therefore, it will be 1 and it will be 0. Whenever trigger applies, it will be unstable. This is unstable. It will enter into stable state. Right? If you observe clearly, maybe instead of taking your output, you can take one more inverter, then it will be followed as Q. If you observe clearly, whenever trigger applies, let us say this is what is the trigger which you are getting from microcontroller. Then I want to give this to a LED. Then if you give very small trigger pulse, LED cannot detect it. Then it cannot flash the light. Then I want to increase the stretch. I want to increase the pulse width. Whatever width you have, I want to increase it. If you observe clearly, whenever, let me speak with respect to Q or Q bar, maybe you can take one more inverter, then you'll get exactly Q. Now if you see here, whenever there is a negative pulse, this is what your trigger pulse. Now we have this much width, right? Again, whenever there is a negative pulse, this is what is your negative pulse. Therefore, if you observe clearly, from here to here, it is a pulse stretcher. From here to here, it is a pulse stretcher. Whatever negative pulse you have, that is what is stretched indirectly. Negative pulse stretched. Therefore, with respect to your trigger, whenever trigger applies periodic way, right, or whenever trigger comes, the small trigger pulse will be stretched. Then you are going to get whether it is inverter or non-inverter, whatever may be. Therefore, this is what is called pulse stretcher. This is what is called pulse stretcher. Whatever pulse you want to stretch, that you apply as a trigger, then that pulse, the trigger pulse will be stretched, and that is what you will get it. Therefore, this is what is pulse stretcher. This is over, right? Therefore, whatever pulse you want to stretch, apply as a trigger, then you will get output as pulse stretcher. Okay? Take it. This is done. You will be confused if I explain with respect to Q bar. That's why I'm explaining with Q. Maybe if you take one more inverter, it is exactly same as this. But whenever negative pulse comes, if you want positive pulse stretch, that is also fine. That depends on the application. This is interesting, but we need to, even though circuit looks bigger, but it is easy to understand, okay? Because it is comparator and flip-flop. I'll give you 2 more minutes. After that, I'll start problem number 24. Classroom problem 24. And after that, I can say simplify timer is over. Then we can go to workbook problems. Okay? Now we can take chapter 4 as entire chapter, then we need to solve the problems related to all different topics. Whatever trigger pulses period you have, the same period you are observing at Q also. Therefore, the period is not changing. Therefore, the pulse is stretched. But here the on time of your trigger is very high, it's high. Here the on time is decreased because your negative pulse is stretched, therefore your total period is constant, therefore obviously your on time will decrease. But how much stretch you want, that depends on the charging time. Therefore indirectly that is depending on the R value, right? How much you want to stretch, that depends on R, which is nothing but 0.69 RA into C, or R into C. That is what is your charging time constant. Can I say 0.69 into R into C? No. If I represent with respect to 0, right, then from 0 to 2/3 VCC you need to calculate, not 1/3 VCC to 2/3 VCC. Okay? But qualitatively I can say it depends on the charging time constant. But don't use the formula 0.69 R into C. That 0.69 R into C is valid only for 1/3 VCC to 2/3 VCC, or 2/3 VCC to 1/3 VCC. Only the delta from 1/3 VCC to 2/3 VCC. But here it is 0 to 2/3 VCC according to this timing waveform. Done? Okay. Can I erase? Problem number 24, classroom workbook problem. In the stable multi-vibrator circuit shown, the frequency of oscillation at the output pin 3 is, see, the complete circuit is not given, but you are supposed to know, and I have given already what is the internal circuit, okay? The pin diagram is given. This is what is VCC, and this is what is reset, and this is what is pin number 8, and this is what is pin number 4. Both are VCC. Okay, this is what is given, and this is out, which is pin number 3. He has given pin numbers outside. Okay, but what I explained is pin numbers inside and then output description. Okay, this is what is 7, this is 6, this is 2, this is trigger, this is threshold voltage. It has given like this only, and discharge DASCH, and this is ground, pin number 1. Okay, and now external circuit is, this is 8 connected with a resistor, then one more resistor and capacitor. Okay, this is what is given. This is RA 2.2K, RA, this is 2.2 kilo ohm, RB 4.7 kilo ohm, and C 0.022 microfarad. This is what is given. Okay, now asking for, this is a stable multivibrator. Yes, we know that this is a stable multivibrator. A stable multivibrator. Now asking for frequency of oscillations. Therefore, asking for resonant frequency. Okay, this is fill in the blank. This is GATE 2016, set 3 for 1 mark. 1 mark. Okay. Now let's see. We know this, right? Therefore, according to us, this is nothing but a stable multivibrator, and this is what is your charging time. This is your charging time. This is your charging time. And where is your discharging time? Discharge. This is discharge 7. Therefore, this is what is your discharging time. Right? Then tell me, what is your on time? Therefore, on time is equal to 0.69 into tau C, charging time. Therefore, 0.69 into, what is charging time? RA plus RB into C. Similarly, what is your off time? Your off time is equal to 0.69 into discharging time. Therefore, 0.69 into, what is discharging time? RB into C. Therefore, what is your total period? T is equal to T on plus T off. Therefore, what is T on? T on is nothing but 0.69. If you take 0.69 common, 0.69 RA plus RBC, RBC, then 2 RBC. Therefore, 0.69 RA plus 2 into RB into C. Then what is your frequency? Frequency is equal to 1 by T. This is what your frequency of operation. Therefore, 1 divided by 0.69 into RA plus 2 RB into C. This is what is the frequency of oscillation. Okay. You substitute, you'll get the answer. If you want, answer is 5.68 kHz. Therefore, F naught is equal to 5.68 kHz. This is the answer, because this is fill in the blank. Okay. You know RA 2.2K, 2 RB 9.4 plus 2.2, 9.6, 11.6 into 0.022. If you do it, you'll get 5.68 kHz. Therefore, with this chapter 4 concept is over. We can go for workbook problems. From next session, if this is over, fine. Else you can pause the video and then copy it. Then you'll get it. If you understand the procedure, you try to solve on your own. Okay? Done. Thank you.